Lab 5, Energy Expended by a Dog Rolling Over. For my Choose Your Own Adventure lab, I decided to analyze the energy expended during translation and rotation of my dog rolling over. My dog's favorite treat is a mini marshmallow, which she receives every time she does a trick like rolling over. But she is somewhat overweight, so the purpose of this lab was to determine the number of times my dog needs to roll over to burn off the chemical potential energy in one mini marshmallow, using Newton's second law to determine force and work she does for translation, and the energy principle to determine the work she does to rotate. To do this, I filmed the roll directly from above, tracked the movement, calculated changes in internal energy, and compared this energy with the energy in one mini marshmallow. After doing this, I found that it takes 1,114 rolls to burn off one treat. Let's discuss the foundation of the analysis. The first fundamental principle I use was Newton's second law, which deals with center of mass motion and says that net force equals mass times acceleration, where acceleration equals change in velocity divided by change in time. I used this information to solve for net force in each frame using the change in velocity specific to that time interval. I then used a piecewise approach to determine the work of translation by summing the net force times change in position for each frame throughout the interval. Newton's second law was only useful to me for center of mass motion, so it could only tell me about change in internal energy due to translation of the roll. I also needed to consider energy needed to cause rotation. For this, I used the energy principle, which says that net work equals total change in energy of the system, which equals the opposite of the change in internal energy. I was interested in work needed for the roll, which includes work of translation and work of rotation. I previously solved for work of translation using Newton's second law, so now I needed to determine work of rotation. We know that it takes energy to speed up to start the roll, but we also know it takes energy to slow down to a stop. So we get this equation for work of rotation. To do the analysis, I decided to assume that work of rotation is constant throughout the interval, and that it takes equal energies to start at rest and speed up to a maximum rotational velocity, then slow back down to rest from that maximum speed. In thinking this way, we find this equation. We know that rotational kinetic energy equals 1/2 times moment of inertia times angular speed squared. I was able to determine average angular speed knowing that she rolled 2 pi radians in a certain number of seconds. To determine I made a simplification. My dog is a miniature dachshund, so when she rolls, her shape is very close to a cylinder. Moment of inertia for a cylinder equals 1/2 times mass times distance from rotational axis squared. I was able to determine the radius of the cylinder by measuring her circumference at several places around her body, then averaging and dividing by 2 pi. Let's now take a look at the video. In order to obtain real position and time data, I chose this axis system, with the positive x direction being to the right and the positive y direction being up. In this coordinate system, the video is being filmed from the z-axis. To orient the axes in the correct units, I calibrated the length of the row to be 0.6636 meters. You can see that I tilted the axes because she rolled diagonally. I put the origin of the axes at our center of mass in the first frame and tracked her center throughout the entire time interval. The tracker gave me this position and time data to work with in my code. Let's discuss the goals of the code. What I wanted the code to do was first import the x and y position data from tracker, then use this data to calculate the velocity. From there, I wanted to determine net force in each frame using the momentum principle and put all those net forces into a list. From there, I wanted to backtrack and use the net force to model motion by starting at rest and the origin and updating velocity and position for each frame based on that force. From there, I wanted to calculate work of translation by summing the force times change in position for each frame. Then calculate work of rotation and add it to work of translation to get total work, which equals negative change in internal energy. From there, I wanted to calculate the energy in one marshmallow and compare with the energy expended in one roll. Now let's look at the code. Here I inputted the mass of my dog and time step delta t as the number of seconds between frames in the video. I then set it up to read in the x and y positions I got from tracker. Here I set up lists to hold a calculated x, y, and two-dimensional velocity from the following loop. First, it determines change in position as the position from one frame minus the position in the frame immediately before it. Then it calculates the velocity as change in position over change in time. Here it does the same thing for the y position. It then takes the magnitude of the velocity in the total xy plane. Now to calculate the work done for translation. This loop goes through the velocity list for each frame in the video, calculates change in velocity, calculates net force in each frame by Newton's second law, and adds the force in each frame to a list. From there, I used indexing to pull out the change in position for each particular frame. Lastly, I determined work of translation by adding up the force times change in position for each frame. Next, I backtracked and used the calculated forces in the list to make a model of position based on the forces using Newton's second law. Here I initialized the position and velocity to 0. Then I pulled the correct force for each frame using indexing, updated the velocity using Newton's second law, updated position using each calculated velocity, and plotted it. The last chunk of code calculates work of rotation. First, I calculated my dog's average radius using her average circumference, then moment of inertia modeling her as a cylinder. I also inputted average angular speed knowing she rolled 2 pi radians in 1.267 seconds. Next, I have kinetic energy of rotation and work of rotation using this equation as previously discussed. Lastly, I had work of rotation and translation to get total work. We know by the energy principle that work of translation and rotation equals change in energy from these processes, which equals the negative change in internal energy. Next, I calculated the amount of energy in one marshmallow in joules by knowing there are 100 kilocalories in 2/3 of a cup of mini marshmallows. 62 of these marshmallows fit into a 2/3 measuring cup, and one internal kcal gives 4,186 joules of energy. Lastly, I knew that I wanted change in internal energy in one roll times number of rolls plus the energy in one marshmallow to equal 0, and I put this into the code by solving this equation for the number of rolls. When I run the code, here's what I get. You can see the translational motion of my dog here and her trajectory as predicted using known net force extracted from the position data. The final result was that translational work was 5.82 joules, rotational work was 0.24 joules, and total work was 6.06 joules. The number of rolls needed to burn off one marshmallow was 1,114. Here you can see that the graphs of position versus time in the model based on known force and the graph from tracker were identical. This is just application of Newton's second law using a known force. We would expect them to match in this way. There were several potential errors in my approach to this lab. Firstly, I simplified my dog to a cylinder to calculate rotational kinetic energy when she is not perfectly cylindrical, so this will decrease accuracy. I also used average angular speed in this calculation when it could vary significantly throughout the interval. I did not take into account her basal metabolic rate, meaning I did not consider the amount of energy she burns just by being alive. I searched for a conversion efficiency factor to account for efficiency of conversion from ingested calories into energy for work, but I couldn't find one. It is possible that the marshmallow will be largely excreted as waste rather than becoming energy for work. There are other pathways it could also follow, like being stored into fat reserves. A major assumption that I made was that work of rotation will be roughly constant throughout the interval and that it takes equal energies to start from rest and speed it to a maximum velocity, then go from that maximum velocity back to rest. This is likely not true, though we would expect to see an inverted U-shaped function if plotting angular speed versus time. The inverted U is just likely not to be a perfect normal distribution. The last major assumption I made was that other types of energy transfers caused by the roll in the brief interval would not be significant. For example, I did not consider friction or change in thermal energy. Overall, this was an interesting lab, but the findings are limited by all these assumptions.